Now, yesterday we talked about some rules for the order that the hogs go into the hog Hilton. Today what I want to do is to go over what the chemical names are for the electron configurations, but you're going to find that the rules are very similar. The first rule is called the Pauli Exclusion Principle, and it states that each orbital can hold only 2 electrons, and those 2 electrons have to have opposite spins. Now this was the rule yesterday about the hogs sleeping 2 to a bed. If you force them to sleep in the same bed, one's going to sleep with his head up at the front, at the top. The other one's going to sleep with his head down at the foot. So remember, we always drew our hogs tail to tail. They never faced each other. With electrons, it's the similar kind of thing. We say that they have opposite spins. Electrons literally spin around in space in the electron cloud. And the reason that we have them with opposite spins is so that they aren't identical. We have to be able to tell them apart somehow, some way. So they're in the same orbital, they're in the same sublevel. We've got them going 2 different directions to be able to tell them apart. Now, by convention, the first electron in the orbital is always going to be drawn right side up, like the one on the left here. The second one that goes in the orbital is always drawn upside down, like the one on the right here. The second general rule is called the Aufbau Principle. Aufbau is a German term that means building up. This was the lazy hog rule. We said yesterday that the hogs don't like to climb stairs. So they're going to take the first room available on the lowest floor. It's the same thing with electrons. You will always start your electron configurations with the 1s orbital. Electrons fill the 1s first. If you look at this diagram, 1s is on the very bottom. That is the lowest energy level in an atom in the electron cloud. Now once the 1s is filled, 2s comes next, and then 2p, and then 3s, and then 3p, and so on. So it follows the same pattern that we used yesterday for the hog Hilton. But that's called the Aufbau Principle. The third general rule for writing good electron configurations is called Hund's rule. Sometimes Hund's rule is called the empty bus seat rule, but yesterday when we were drawing the hog Hilton configurations, this was the rule that said that hogs don't like to share their rooms with other hogs. Now if you look at the pictures at the bottom, the one on the left is wrong because in the first room there are 2 electrons. In the middle box there are 2 electrons, and on the right there are no electrons. A better configuration would be the one that's drawn on the right. You have the first electron in the left box right side up. The second electron is the one that's in the middle box. The third electron is the one that's on the right hand side. And the fourth electron is the one that's upside down in the first box. So the Hund's rule tells us that electrons won't pair up in a sublevel until they're forced to. Okay, now let's look at all the different types of notation that we have for telling how electrons are inside the cloud for an element. Here's the orbital diagram for oxygen, as well as its electron configuration. Now oxygen is in box number 8 on the periodic table, so it has a total of 8 electrons. If you look at the order of filling from the hog Hilton notes, remember that the 1s sublevel is the first thing that gets filled up in a configuration. 1 is the lowest energy level, and s is the type of sublevel that's there. I can put 2 electrons in the 1s orbital for oxygen. No more will fit there. So the next thing that gets filled up is to go to the second energy level and fill up the 2s. I can put 2 electrons there, but no more. Once the 2s is full, there's still some more rooms on the second floor. The 2p rooms are available, or the 2p sublevel. You represent the 2p with three dashes, or 3 boxes like here on the screen, and you put the electrons in the boxes one at a time. So the first electron in the 2p is the one on the left that is right side up. The second one is in the middle box, right side up. The third one's on the right hand side, right side up. And the last electron for oxygen goes in the first 2p box, upside down. Now those orbital diagrams can be written in a shorthand way as an electron configuration. I've tried to color code it for you. Look how the green orbital diagram becomes the 1s2 part of the configuration. And then the yellow 2s becomes 2s2, and the pink 2p becomes 2p4. The big numbers in front of the letters represent the energy level. The letter represents the type of sublevel, and then the numbers that look like exponents tell you how many electrons are in each one of those sublevels. Now the type of electron configuration that you've been writing for these elements is called the longhand electron configuration. It's longhand because it shows every electron in the entire electron cloud for the atom. But if you look at this representation for sulfur, not all of the electrons for sulfur are active. The valence electrons in yellow are the electrons that do the chemistry for the element. The core electrons, the green ones, are buried deep inside the electron cloud, and they don't do any chemical reactions. Now, valence electrons are defined like this. Make sure you write this down. Valence electrons are the highest energy level s and p electrons for an element. I'll tell you again. Valence electrons are the highest energy level s and p electrons for an element. So when I look at the longhand configuration for any element, I'm going to find the largest number in front of the letters. For sulfur, it's 3. The 3s and the 3p. And I'm going to add all those electrons together. There are 2 valence electrons in the 3s. There are 4 valence electrons in the 3p. Those electrons added together give me a total of 6 valence electrons for sulfur. Now, you can write even a shorter notation for elements and their electrons. If you look at the bottom, there's a noble gas configuration for sulfur. Now, the easiest way to teach you how to do this is to have you look on the periodic table while I explain it. I want you to find sulfur. Now, sulfur in box number 16, we just drew the longhand notation. It's got all 16 electrons. If you take your finger and go backwards on the periodic table until you get to a noble gas that comes before sulfur, and noble gases are group 18, remember, you're going to come to neon, element number 10. You can replace the first part of the configuration for sulfur with neon in brackets. So the green at the bottom where it says neon tells me that you are representing the 1s2, 2s2, 2p6 electrons for sulfur. And I color-coded it green to show you that. Now once you write neon in brackets, you just have to write the rest of the electrons. 3s2 and 3p4 come at the end. So the nice thing about noble gas configuration is that it shows the valence electrons at the end of the configuration. One rule for noble gas configuration. The element that goes in those brackets, like I have neon right there, must be from group 18. It has to be a noble gas. And sometimes students ask, what if the noble gas configuration is for a noble gas? You have to write the noble gas that comes before your element in the brackets. Now if that's a little confusing, don't worry, that's just another way to write the configuration. Okay, let's review what we know about the periodic table and the patterns that we see for the electron configurations. The period number, those big numbers that go down the left side of the table, those tell you what energy level the outermost electrons are in for an element. Don't forget you have to subtract 1 for the D's and 2 for the F's. The block that the element is in, S, P, D, or F, tells you the sublevel. S's are on the left side of the table, groups 1 and 2. D's are in the middle, groups 3 through 12. The P's are groups 13 through 18. And the F's are the 2 rows across the bottom, lanthanides and actinides. If you're trying to figure out how many electrons are in a particular sublevel, look at the number of electrons. How many columns over is it? For example, calcium is in the second group. It's an alkaline earth metal. It's in the second column of the S block, so its configuration ends in S2. If you look at the oxygen that we did earlier, oxygen's configuration ends in 2p4. If you start on the tall section of the P block with group 13, oxygen is in the 4th column over. That's where the 4 in 2p4 comes from. Here's a review of what the letters and numbers in the configurations mean. The big number in front of the letter tells you the energy level or the period. The S tells you the block, and then the exponent looking number tells you which column of that block each element is in. And I've shown you the one for hydrogen. The first row, S block, first column. Now if you're a little bit confused on how to know how to write the configuration without having the Hog Hilton in front of you or without just memorizing it, let me remind you of what the pattern is on the periodic table. You can write this in on the periodic table that we colored the other day. The S block of the periodic table are the first 2 tall columns on the left-hand side, group 1 and group 2. Those are the alkali metals and the alkaline earth metals. The first row in the S block represent the 1s elements. The second row in the S block represent the 2s elements. And all the way down to the bottom where francium is, it's in the 7th period, so it represents the 7s configuration. Now when I say it represents that configuration, what I'm talking about is that the configuration for that element ends in that number and letter. So francium, for example, would end its configuration in 7s1. The next section of the periodic table that's colored green on this screen are the D block elements. Now the trick to identifying the D block elements is that the first row appears to be the 4D, but you know that the first place you see a D in the electron configuration pattern is a 3D. So the thing you have to remember about the D's is to subtract 1 from the row that it's in. So now look at the way these are labeled. The 3D row is actually in the 4th period of the periodic table. The 4D is actually in the 5th period. The 5D is in the 6th period, and the 6D is in the 7th period. You have to subtract 1 from the period that the element is actually in to be able to figure out which D you're using. The tall section on the right side of the periodic table is called the P block of elements. Beginning with group group 13 through group 18 are the elements that are p-block elements. The energy level is the row or the period that they're in. The F-block elements are the elements that are down at the very bottom of the table, the lanthanides and the actinides. The trick here is that you have to subtract 2 from the period number that they appear to be in. Along the first row of the lanthanides, if we took that entire section of the periodic table and we put it up in the main section of the table where those stars are with lanthanum and actinium, you would see that it looks like the lanthanides are in 6th period, the actinides are in the 7th period. But if you subtract 2, you get 4 and 5. So the lanthanides actually are using the 4F, the actinides are actually using the 5F. Take a minute to label those things on your periodic table. Here's another view of the periodic table. The nice thing about it is that the lanthanides and the actinides have been pulled up into the main part of the table. Remember to write those shorthand configurations. The core electrons are the ones that are buried the deepest in the cloud. They don't do any chemistry. The ones you're going to be interested in from here on out are the valence electrons. Those are the highest energy level S and P electrons for an element. They're the outermost electrons in the cloud. They're the ones that are going to do all the chemistry.
If you look at this animation online, we start with hydrogen. There's 1 electron in the 1s sublevel. When we add the second electron to make the element helium, the second electron goes in the 1s also. But then that sublevel's full. So look what happens next. The third electron adds to the 2s. The fourth also in the 2s, and then that's full. So as I go to boron, remember we talked about the rules of filling. We're going to put 1 electron in each one of those 2p orbitals, then we go back and fill in the second electron in each one of the 2p orbitals. After neon, we start the third period, so we go into the third energy level. We're going to fill the 3s first, followed by the 3p, using those rules for filling. After argon, which is a noble gas at the end of the third period, we're going to go and fill the 4s sublevel with potassium and calcium, followed by the 3d. Now chromium does an unusual thing. We'll talk about that later. And copper does an unusual thing. You can follow this pattern with the pattern of the Hog Hilton and the pattern that I gave you in your notes for all of the elements to see that this order of filling does hold true.
Okay, let's see if we can review the noble gas notation. The element that I've picked for your example is germanium. It's in the beige box that's on this periodic table. Find it on your periodic table. Now, if you move backwards on the periodic table, back through those green elements in the D block, back through those yellow elements in the S block, you will come to the noble gas argon. That is the nearest noble gas that comes before the element germanium. So you write argon in brackets, and you've got to write everything that comes after argon to finish the noble gas notation. Well, argon is element number 18. So 19 and 20 come next. Those elements are in the 4th row S block of the periodic table. So you write 4s2. The next set of elements, numbers 21 through 30, are in the 4th row, the D block. So I subtract 1. 4 minus 1 is 3. I write 3D for the block, and there are 10 blocks that I count in that section. So I say 3D10. Then I write 4P. I'm in the 4th row of the table in the P block of elements, and germanium is the second block in that section. So I write 4P2. That's the noble gas notation for germanium. Okay, let's stop for a minute and let you practice. I want you to work with the people at your table. See if you can do these 3 items. Draw the orbital notation, which is with the squares or the dashes and the check marks for electrons. The electron configuration for iron. The electron configuration is the 1s2, 2s2, 2p6 format. See if you can figure out where the valence electrons are for iron, and then see if you can write the noble gas configuration. That's the one that I just showed you, where you write the noble gas that comes before the element in the brackets. And I'm going to give you about 5 minutes to work on that. Okay, let's check your answers. Here's the orbital notation. If you look at iron's position on the periodic table, it's element number 26. So you need a total of 26 electrons in your orbital notation. Now I've drawn them all out, but I wasn't able to do a very good job labeling them for you. So I'm going to go through and tell you what each blank represents. The first blank is the 1s. The second blank is the 2s. The next 3 blanks all together make up the 2p. The 6th blank represents the 3s. The next group of 3 lines represents the 3p. The final blank on the first line represents the 4s. The group of 5 blanks on the second row here represent the 3D sublevel. If you compare that orbital notation to the electron configuration, the letters and numbers should match up. The electron configuration for iron is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. Check now to make sure yours is the same on your paper as mine on the screen. The next part of the question is for you to determine where the valence electrons are for iron. Remember that valence electrons are the highest energy level S and P electrons for an element. So first, look at the configuration. Find the biggest energy level. Those are the big numbers in front of the letters. I've indicated in red where those are for iron. The 4th energy level is being used. That's the highest energy level. So the S and P electrons in the 4th energy level are the valence ones. Now for iron, there is no 4p in the configuration, but you do use the 4s, so those 2 electrons there in red are the 2 valence electrons for iron. Now to write the noble gas configuration for iron, find iron on the periodic table, move backwards on the table until you get to a noble gas in group 18. That should be argon. So I've written argon in brackets, and I still have to write the valence electrons. Everything that comes after argon in the configuration needs to be rewritten. 4s2 and 3d6 will get you right back to iron on the periodic table. Take a minute to make sure your noble gas configuration matches mine. Now, see if you can check yourself. Try and write the electron configuration for the element tellurium, that's the symbol Te, only using the periodic table. Start up on the first row where hydrogen and helium are and write down the period, the block, and how many elements you're looking at for each row of the table. When you finish, you should have a longhand configuration for tellurium. Reading the table in rows, just like lines in a book from left to right until you get to the element tellurium, should work for you. See what you get. Alright, here's the answer. I want you to follow on the periodic table as I go through this configuration with you. When I start at the very top of the periodic table on the left side, I'm in the first row, the first period. That represents the elements hydrogen and helium. So I write 1s2. The first row, the S block, there are 2 elements. Then I drop down to the second row of the periodic table, and I've got 2 S elements there, so I write 2s2. That's lithium and beryllium. Then I go across to the 2p sublevel. I'm still in the second row, but the P block, and if you count, there are 6 elements in that section of the periodic table. You start with boron, and you go all the way across to group 18 at the noble gases. Then I drop down to the third row of the periodic table, and I start with elements 11 and 12. They're in the third row, the S block. There are 2 of them, so I write 3s2. Then I continue on. I go over to the third row, the P block. I write 3p, and you count, there are 6 squares there. Those are the elements from numbers 13 to 18. Then I drop down to the 4s. 4s, there are 2 elements there in the fourth row, so I write 4s2. The next element that you run into is scandium, element number 21. It's in the fourth row, but it's a D block. So you subtract 1 and you write 3D. Count the squares across in the D block. There are 10 of them. 3D10. Next comes the P block again. You're in the fourth row, so you write 4P. There are 6 elements there, 4p6. Then you wrap back around to the beginning of the table, 5s. The fifth row, the S block, there are 2 elements there, so you write 5s2. Then you're at a D block again. There are 10 elements there, but it's not the 5D. You subtract 1, it's a 4D. And then you write 5p, you're in the fifth row, the P block, and tellurium is the 4th element across. Now, you can check your work by adding up all those little exponent numbers. They should add up to the atomic number of tellurium. Take a minute to do that and let's see if we're right. Tellurium should be element number 52. If what I've typed on the screen adds up to that, you've probably done it correctly. Let's go through it one more time, and as I read the configuration, try and follow it on the periodic table. The electron configuration for tellurium is 1s2, next row, 2s2, 2p6. Third row, 3s2, 3p6. Fourth row, 4s2, 3d10, 4p6. Fifth row, 5s2, 4d10, and you get to tellurium at 5p4. Now here's some new notes. I don't think you have any of this before right now. Why do we care about the way electrons are put in an electron cloud? What difference does it make? Now, you might not care, but I need to tell you. The reason that the configurations matter is because they tell us if an element is going to be reactive or not. Here are the order of stability for different configurations. You see how some of the boxes in the periodic table are outlined in white? The ones that have the full energy level are the most stable elements of all. Now which group outlined there in white has the entire energy level filled up? If you guess group 18, you're right. The noble gases have completely filled energy levels. They are the most stable elements of all. Now when I say they're the most stable, what that means is they don't react with other elements. In fact, that's where they get their name, noble gases. They act like nobility. They don't interact with the common folk elements. The next order of elements that shows some stability are the ones that have a full sublevel. A full S, like S2, a full P, P6, a full D, D10, or a full F, F14. Those are the most stable configurations in a sublevel. So group 2 is outlined in white, the alkaline earth metals. Group 12, where zinc is, have a little bit more stability than others because they have a full D. The noble gases we've already talked about with a full P. And then the full Fs are on the very bottom in the lanthanides and the actinides on the very right hand side. The final configuration that gives a little bit of stability to an element is if the sublevel is half full. The D5s are outlined in white here, the P3s, and the F7s. If you think about the orbital diagram, you'll see where the stability comes from. D's have 5 blanks, and if the element has 5 electrons, there's 1 electron in each one of those orbitals, so it's half full. That makes it a little less reactive than other elements' configurations will be. The P3s do the same thing. If you look at the orbital diagram for a P, you draw it with 3 blanks. So the P3s have 1 electron in each blank. It's exactly half full, and that gives it some extra stability. The F7s are the exact same way. 7 blanks, 7 electrons. So what you need to remember is this order of stability. The full energy level, the noble gases, are the least reactive. Full sublevels are the next level of stability. And finally, half-full sublevels. If an element has none of these configurations, it just doesn't have extra stability. It's probably an element that will do some chemistry and some chemical reactions. Here are some exceptions to the rule for stability and the rule for writing configurations that we've been working on. For a lot of rules in chemistry, they are just rules, not laws, and there are exceptions. You're going to get tired of them sometimes. But these aren't too bad. Hopefully I can show you the rule and you'll be able to pick up on it. The first exception that I want to show you is copper. Okay, so find copper on the periodic table. The noble gas notation that I've written first is what you would expect copper to be. its configuration ends in 3D9. It's in the 4th row of the periodic table in the D block, and it's the 9th block over in the D block. So that's what you would expect. Now if you go back and look at the rules for stability, there's nothing special about copper's configuration. D9 is not half full, it's not completely full. But if copper could get just one more electron in that 3D sublevel, it would be completely filled. That would add stability to copper. So what copper does is it promotes one electron from the 4s to the 3d. If you look at the numbers in the exponent place, you'll see how that happens. Instead of 4s2, copper actually gives a 4s1 configuration, and that one electron that's been lost gets moved up to the 3d. So instead of 3d9, we see 3d10. The only reason that this happens is because it gains stability the exact same way. Now, if copper does it, what other elements do you think might do this? Remember, the periodic law says that elements in the same group have similar properties. So look at the elements below copper. Those elements will also add one electron to their D sublevel to gain extra stability. Here's the last exception to the rules for electron configurations. The element that I'm going to show you this time is chromium. Chromium's going to do something similar to what copper did. In fact, copper, silver, and gold. Remember, you looked at that whole group on the last slide. Well, chromium, you would expect to have a configuration that ends in 3d4. It's in the D block, the 4th element over, and it's in the 4th row. So you see how the end of the configuration is 3d4. Well, there's nothing special about that configuration. Chromium doesn't have stability because of it. But if chromium could just add one more electron to its 3d sublevel, it would be half filled. So kind of imagine what a 3d4 looks like. There are 5 blanks there, and you've got 4 check marks, one in each of the first 4 blanks. So that last orbital is empty. If you could put one more electron there, you would have that sublevel half filled, and that would make chromium more stable. Well, elements like their stability, so it wants to do that. What happens actually is that chromium moves one of its electrons from the 4s up to the 3d, just like copper, silver, and gold did. So instead of the 4s2 configuration, you see 4s1, and instead of 3d4, you see 3d5. I'm going to ask you the same question that I asked before. If chromium does this, what other elements would you expect to see it happening with? The periodic law does tell us that elements in the same group have similar properties. So if you guessed tungsten and molybdenum, you're right. Chromium, tungsten, and molybdenum all promote one electron to the 3d. These are the only 2 places that you will see these exceptions, the D4s and the D9s. So don't get carried away with it and try and do it anywhere else. Only those 2 groups promote extra electrons. Okay, this is the last bit of it. Hang in there. We've been talking about how elements try and gain stability. It turns out that the reason we see all these patterns in elements trying to become stable is because their ultimate goal is to look like the noble gas configurations. Remember, I told you noble gases were kind of like nobility in that they don't do any chemistry, they don't interact with other elements. Well, everybody wants to be like them. So the ions that you see forming when elements have charges with them, we talked about ions earlier in one of the last units about how when you count protons, neutrons, and electrons, if an element gains or loses electrons, you get these ions formed. Well, they do it according to a pattern. Atoms gain or lose electrons to get more stability. They're trying to look like the configuration of the noble gas that's nearest to them. Now, if you look on this periodic table, I've listed the charges across the top for each group on the table. And you can write this on the table that's in your reference packet if you want to, or in the table that we colored last week. Group 1 makes +1 ions. Group 2 makes +2 ions. Now, I didn't put a charge on top of the D block, the green section of the table here. If you ever have to guess, you can guess +2, but what we're going to learn later is just like everything else, there's an exception to the rule. Now for group 13, those elements are going to form a +3 charge. Group 14 is right in the middle of the table. They can be +4 or -4 ions. Group 15 forms -3 ions. Group 16 -2. Group 17 -1, and Group 18 is 0. Now that is a pattern in and of itself, but the reason that that pattern exists is because of the elements trying to look like noble gases. Think back to what a -1 means. You add one extra electron, right? So look at fluorine on the periodic table. Fluorine's in Group 17, one of the halogens. If fluorine had just one more electron, it would look like a noble gas, right? So that's what fluorine does. It gains one electron so that it looks like a noble gas. And if fluorine does it, every other halogen does it too. Now let's go back over to an element on the left side. Take lithium, for example. Lithium's in Group 1. What does a +1 ion mean? You remember that that means the element has lost one electron. So if you take lithium's configuration and remove one electron, you move backwards one square on the periodic table. Lithium would look like helium, a noble gas. Every other element in all the other groups do the same exact thing. They lose or gain electrons so that they look like the same configuration as the nearest noble gas. Let's look at an example of an ion's electron configuration that I was telling you about in the last slide. Here's the electron configuration for the oxygen ion. Now if you find oxygen on the periodic table, it's element number 8. That means it should have 8 electrons. The configuration for the oxygen atom is one that we've already written. It should be 1s2, 2s2, 2p4. Think about how oxygen can get a noble gas configuration. Count the squares going forward to group 18, or count the squares going backwards to group 18. The atom is going to do whichever path is easier. In oxygen's case, it's easier to gain 2 electrons so that it looks like neon. Instead of 8 electrons, we find oxygen ions with 10 electrons. So instead of the configuration ending in 2p4, it ends in 2p6. The oxygen ion has a total of 10 electrons, just like neon does, and that gives it extra stability. See if you can do this one. Try and write the electron configuration from calcium just by looking at the periodic table, and then see if you can figure out what calcium does when it becomes an ion to look like the nearest noble gas. When you finish working with your table and talking it over, we'll check your answer. Okay, here it is. Calcium's element number 20. So my exponents in the configuration add up to 20. The configuration should read like this: 1s2, 2s2, 2p6, 3s2, 3p6, and 4s2. Calcium is in the fourth period, the S block, the second column. Now for calcium to become the calcium ion, you need to count the squares going forward to the noble gases in group 18 and count the squares going backwards to the nearest noble gas in group 18. For calcium, the easier way is to go backwards. If calcium can give away 2 electrons so that it only has 18 instead of 20, it'll look like a noble gas. So the configuration for the calcium ion is 1s2, 2s2, 2p6, 3s2, 3p6. Now which noble gas does that look like? Alright guys, we are all done. I know your brain's probably full, and I really appreciate you taking these notes. Don't worry about being confused on part of it. It definitely takes practice, and I'll be able to answer a lot of your questions on Monday. What you do need to do is write down the questions that you have so that you don't forget them when I get back.